Hi everybody, my name is Yana Segal, and today I'm going to talk to you about how we used to build machine learning models and how we build them now. Or more specifically, the long tedious manual procedure we had that turned into a simple three-stage procedure which is also fully automated, scalable, and highly visible. So after that short introduction, hi, my name is Yana Segal. I am a machine learning engineer at Nielsen, and today I will be talking to you about how we automated our machine learning pipelines using Kubernetes and Airflow. The three main points I want to talk to you about is how we utilized Kubernetes benefits and strengths to do this automation. The second point is how we used Airflow to boost this transition. And the third point is some things or some points we wish we knew before we began and could have facilitated our transition to the new automated pipeline. Okay, so a little bit about Nielsen. You might know Nielsen as the rating company in the United States, but Nielsen is actually a data company. And we use that data to build the machine learning models to give our customers insights on their users. For example, we will use a machine learning model to build segments on users, for example, people who like to buy shoes or people who love dogs. And our customers can utilize those segments to boost the performance of their marketing campaigns. Okay, so a little bit about the team. I'm located in the Tel Aviv branch of the company, and the team lead and the solution architect is Arun, and he is located in the NYC branch. We are usually working with typical machine learning tools like Scala, Spark, and Python, but recently we have started to use Kubernetes and Go, as we will see in the next slides. Okay, so how did we use to build models? In the first stage, the user, usually a data scientist, will write a configuration file for all the models he wants to build. These models are called group models because they have some similar features. These configuration files will typically look something like that. Here's the group name, which is consistent through all the rows. The model name, we have here 3 different models, and each model has its own steps that we want to run in the machine learning pipeline to create the model. In this case, models 1 and 3, we only want to run the pre-processing step. But for model 2, we want to run all the steps: the pre-processing, the model fitting, the model evaluation, which includes the confusion metrics, and the reporting stage that collects all the data that was created during model training, and we want it to be sent to the user. So in the next stage, the user launches a Dockerized application we call message producer that reads this configuration file and populates a queue, in our case a RabbitMQ queue, with 1 message per model. And this looks something like that. We have here the group ID, the model name, and most importantly, the machine learning pipeline steps we want to run on this model. In this case, all 4 steps. In the next stage, the user will launch multiple containerized applications we call message consumers. Each application will read 1 message from the queue and run all the steps indicated in the queue for that model. So each message consumer reads from the queue, builds the model, reads another message, and so forth until the queue is empty. So what are the problems with this pipeline? First of all, it requires the users, the data science people, to use tools that are not related to their core business. They should be handling the model improvement and data science related things and not the DevOps related things of this process and repetitive steps. Second problem is the solution is not scalable. Since each user decides how many consumer instances to launch, this is not efficient, and also the user might forget to turn off these machines, and this is simply not efficient. And the third point here is that we don't have visibility, whether it's common errors or how many resources each model requires from the machine. So these are problems we need to solve. So the solution or the new architecture includes Kubernetes and Airflow joint effort. But before I'll show you our new solution, I would like us to get to the same baseline as regards to what Kubernetes and Airflow are. So Kubernetes is a platform that allows you to manage your containerized workflows. Its main or one of its important features is its high scalability. It allows you to scale up and down with ease and have many replicas of the same containerized application and so forth. And another important point I want to stress out is that it has a very popular command line tool called kubectl that allows you to view and monitor and deploy objects inside the cluster. And I will mention it here because we will be using it down the road. So how does the basic unit in the cluster look? This is a node. This is a basic unit of the cluster. A node is simply a compute engine or an EC2 instance if you're working with AWS. And inside you have logical units called pods, and each pod can have its own containerized applications. For example, message consumers we saw in our old solution. Also, each pod has its own internal IP address, and we can reflect that to users outside of the node if necessary. So that's what I had to say about Kubernetes. Now, Airflow. Airflow is a simple platform to manage your workflows, and it is built of a simple component called an operator that represents a single task and is implemented in Python. Let's take a look at an example to have a more clear vision. So this is a simple Airflow DAG. Our DAG is called Hello World, and a DAG is a direct acyclic graph, or simply put, a pipeline with steps. And here we have two operators, a dummy operator and a Python operator that prints Hello World, and the connection between them. First dummy operator, second Hello World operator. And this is how it looks in the UI. Quite simple. Okay, now we're ready to look at the new solution. So in the new solution, the data scientists write configuration files and drop them into an S3 bucket. And this is where their job ends. Now they only wait for a message to be sent to them that the model is built. So we have a bucket with multiple configuration files, which is pulled by an Airflow DAG in a predefined schedule. Once the Airflow DAG finds at least one configuration file, it takes them and populates one queue per group model, meaning each group model will be processed by a different queue and a different workload. The next step, the Airflow DAG launches objects called jobs inside the cluster. Here you can see this job number 1, which is responsible for queue number 1. So all the message consumer pods that will be working on this job will be reading messages from queue number 1. So each message consumer will read a message and then deploy another pod, which is the worker pod, and this is the component that will be actually executed the machine learning pipeline. Once the building of this model is done, the message consumer pod will read another message and so forth. Okay, so how does this solution solve our issues? First, let's talk about automation. How do we actually deploy jobs to the cluster? So the simplest way to do so is by writing a configuration file and deploying that configuration file to the cluster using the kubectl command we have discussed before. So let's look at a few interesting features inside this configuration file. First, the parallelism. Here we indicate how many pod instances should work on the job, in our case 3. Second point is what is the image that the pod should run. In our case, it's a message consumer image. So each one of these 3 pods will be a message consumer. And we'll be taking that image from our Docker repo. The third interesting point is that we can pass an environmental variable with the queue name to the pod, or any other environmental variable for that matter, And that's how the pod knows from which queue to read. Last stage, we can just use kubectl apply on the configuration file and the job will be deployed on the cluster. Okay, so let's look at the pod configuration file and some interesting things here. So first of all, we can create our own custom label that indicates for each worker pod, a pod that executes the pipeline itself, it will indicate to him which consumer pod launched you. And this will be very helpful when debugging or tracking error messages. The next stage, we want this pod, the worker pod, to launch all the step containers of our pipeline, pre-processing, feed, etc., and we indicate the message here. Unfortunately, this solution does not work. Why? Because pod containers are executed parallelly, meaning pre-processing and feed in this case will run at the same time, and this is counterproductive, obviously, because in machine learning pipelines, you will need the output of pre-processing for the feed stage. So we need to solve this. And along comes a parameter called init containers. Init containers is a parameter needed in the pod to prepare the environment before running the real container. And init containers are run sequentially. Therefore, we just move our containers to be init containers. And that's how we bypass this problem. Now, pre-processing, feed, eval, and so forth will run one by one. And the real container will be a dummy container that simply prints I am done or hello world. Another issue we have with this flow is that all the steps currently are hard-coded in the configuration file. But we want each pod to run only the steps indicated in the message. Therefore, what we did is we used Jinja templating. We took a template of this pod configuration file and we added a for loop. So before deploying this pod to the cluster, we will render this template with the steps parameter, which will give us the key and value of the images we need to run inside the pod. So each pod will run a dynamic amount of steps, and this will give us flexibility and solve our issue. Okay, that's all about automation. Now let's talk about scalability. The easiest way to do so is by example. So in this example, we have a pod we want to deploy inside the cluster. This is our cluster. And for now, nothing happens. Nothing happens because we don't have any compute instances or EC2 instances on the cluster. So once a pod is deployed on the cluster, we can run the kubectl command and see that the pod is pending because in the meantime, a node is being spun up. Once the node is ready, the pod will be launched on the node and start running. Nice. Now, what happens if we have another pod that we want to run? If that pod fits the node requirements and the resources that the node can offer, then the pod will be allocated on the same node and start running. If not, a new node will be spun up and the pod will be in pending mode until that node is ready. And once it's ready, the pod will start running on it. Now, how about scale down? Well, as soon as one node's CPU utilization drops under a certain threshold, the cluster knows that the computing on that node is done and will scale it down. And that's how we will reach the empty cluster form we can see here. So this is very resource tight and very efficient, as you can assume. Okay, now let's talk about scalability from the point of view of Airflow. So if you recall, our pipeline was built out of dropping configuration file into a bucket, Airflow triggering, population of queues, and launching one job per queue. Let's translate it to Airflow. It looks something like this. We can see the parallel operators with the steps of the scheme in the first bullet. So here is operator that checks S3 files. Here is an operator that populates the queue by producing messages. And similarly, here is the operators that launch jobs. We have one operator per one job, and each job represents a configuration file. And this is dynamic because each time Airflow polls the bucket, there's a different amount of configuration files there. Unfortunately, this does not work. Why? Because Airflow workflows should be static, or at least slowly changing, like, for example, database schemas. So we can't launch a dynamic amount of job launching operators. What should we do? Well, we know that in Airflow, we can create our own custom operators by extending the base operator and implementing the execute class. Also, fortunately, when we were working on this solution, another team in the company already had their own job launching operator in Airflow. So what we had to do is simply extend this operator to launch multiple jobs in a loop instead of one. Let's see how something like that should look. This is a simplification of our Kubernetes multi-job operator. We have here the task ID, the name of the task, the list of jobs we want to run, job 1, job 2, a job template. This is a template of the YAML file we saw before, and we will populate its features per job. A connection ID, which represents the permissions this Airflow instance has to launch jobs inside Kubernetes, because they need some sort of like handshake and authorizations between them. And the DAG, the direct acyclic graph, this operator belongs to. So now the new solution looks something like this. Instead of multiple launch jobs operators, we only have one. And inside of it, we launch the jobs in a loop. And we are not afraid of the time it takes to launch those jobs in the loop, even if we have 100 or 1000 configuration files, because the action of launching a job in the cluster is very simple. Most of the computation happens afterwards when message producers are, message consumers are launched. So that's good. Okay, lastly, let's talk about how we gained visibility. First, usage visibility. Machine learning pipelines and machine learning steps usually require a lot of CPU and memory resources, and we want to see how much exactly. So what we did is we installed a tool or a platform called Prometheus on the cluster that collects monitoring metrics on all the objects that we are interested in, like nodes, pods, init containers, etc. Next, we paired it with a dashboarding tool called Grafana that collects those metrics and exposes them on a very simple UX-oriented dashboard. This is a very simple architecture of this solution. Here are the various objects on our cluster. Prometheus that also sit on the cluster collects those metrics and sends those to Grafana, and Grafana shows us various dashboards we want to see. Let's look at an example. Okay, here we can see the CPU and memory utilizations of two init containers or two machine learning steps, preprocessing and fit. We can use this in various ways. Let me indicate two. First of all, we can see if our containers behave unexpectedly. For example, if the fit container accumulates memory more and more and more and does not release unneeded memory. So we can debug our resources. And secondly, we can tighten the requested resources by each container, because we see, for example, that preprocessing step only requires 19 giga of memory. So we can ask less than 120 or something like that. So this is a function that Kubernetes allows us to easily install and use on the cluster. Second visibility aspect is error monitoring. To do error monitoring, we use something called ELK stack. There are basically three simple steps for that. First, we install a component called FileBit that collects ORL logs and sends them to Elasticsearch. Elasticsearch indexes this data and stores it. From then, Kibana, the visualization tool, extracts this data and allows us to query it and aggregate it. Let's take a look at the common dashboard we customize. So this is our customized dashboard. We added a column for the pod name because this is a column that is very easy to query on. Also, we added a column with the job name that launched this pod, that is responsible for this pod. So for example, if there's a problem with the job, it will affect all pods and we will be able to see that. And lastly, we have the error message itself. What we can also see here is it is quite easy for people that are not necessarily from R&D to query and debug the issues without having to do any coding or dig deep into the cluster. So this is a very comfortable way to gain visualization on the cluster. In the last slide, I would like to talk to you about all the things we wish we knew before we started and could have made our lives a bit easier. So first of all, Kubernetes is great, but it's also great specifically for machine learning, primarily because machine learning computation requires a lot of resources and in different volumes. So scalability plays a very important part here. Secondly, visualization of our machine learning processes allows us to optimize them and fix various bugs like utilization or common errors. And this is very important, especially when a lot of resources and cost are involved. And this brings me to the third point, the cost efficiency of the solution. Even just from the point of view of having data science be focused on their core business and not do DevOps solutions. And another important point that we learned is that even though our initial solution wasn't efficient, it was divided into small containerized units. And this made our transition to Kubernetes much easier. Therefore, the point here is that if you plan to move on to Kubernetes in the future, you should start building your code appropriately and prepare for that by containerizing your application into small components. Another point, which is more specific, is that we learned that Airflow pipelines should not be dynamic. They should be static or slowly changing. But that's okay because Airflow has other benefits, like you can create your own operators. And with those benefits, you can bypass the issues that are created with the this by design feature. And lastly, we learned that Kubernetes pod containers run in a parallel manner. But that's okay because we, first of all, can bypass that with init containers. But currently, there are also other popular solutions like Argo and Kubeflow. And once we have a working solution with the init containers, we can, in future releases, migrate to more sophisticated solutions. Okay, so I hope you enjoyed the talk or at least learned something new. If you have any questions, please feel free to contact us and have a lovely day. Thank you.